Okay, so let's get started. So today I'm going to continue with the discussion on linear time invariant systems. And I'll go back a little bit and cover the section on zero input response because I went through that a bit fast and I want to talk about real and complex responses separately. And then I'll talk about the system response to an arbitrary input function xt, and which will give us some insights into stability. We'll consider stability in a lot more detail when we talk about control theory. So here I'll just give some kind of intuitive understanding of stability and then move on to transforms, just a brief introduction to transforms, and then really get into the Fourier series. And the Fourier series is sort of the building block for transforms. It's the most intuitive transform. And if you understand Fourier series, you understand Fourier transform. If you understand Fourier transform, you do Laplace. And then with Laplace, you get to Z. And with Laplace and Z, you have all the tools you need to do control theory. So there is this whole progression that we'll start with the Fourier series today. And then the rest of the lectures, which will be probably until the end of next week, will be just on transforms. OK, so let me start with the zero input response. So we have some arbitrary function. And using the functional notation, we can represent this essentially on the form. I'm just going to write down the short form of this, PD, okay, yt equals qd xt, where p and q are polynomials in D, where D is the differentiation operator. And I already wrote out the full form of this last time, so nothing new there. The interesting part here is that the polynomials in D are polynomials on functional forms rather than polynomials in variables that you've seen earlier. So but they still obey the same rules. In particular, you can factorize them as we normally do. To find the zero input response, and by zero input, we actually mean that it's zero other than at the point zero itself. So after time zero, there is no input, but at time zero, we could have an impulse. And in fact, we will have an impulse for there to be any response at all. And so this zero input response is given by setting PD yt equals 0, because the input is over here, and that's 0. And at that point, what we can do is we can factorize this. And the case we considered was when you can factorize this using distinct factors as d minus lambda 1, d minus lambda 2, etc., d minus lambda n equals, this is a polynomial in degree n. I think n is capital N is what I use, with lambda n equals 0. And then this leads to the what I call the characteristic modes. And this general solution is sigma I equals 1 through n ci e to the minus lambda I t, which is a set of complex exponentials because the lambdas belong to the complex plane. So this is a bunch, it's an additive sum of complex exponentials with some factors c sub I. Okay, so this is just reviewing quickly what we did last time. So the two things I want to point out here, the first is that this form is there only because it's a linear time invariant system. Okay, we're getting all this because it's LTI. So we're getting the sum because it's additive. Okay, each individual element over here is a possible solution, and the total solution is going to be the sum because of LTI. And the second thing is that these forms over here, e to the lambda I t, they look like those k e to the sigma plus j omega t that we looked at earlier. And in fact, they are pretty much that. And it's, I should be more careful, sigma plus j omega t. And so these are called the characteristic modes of the system. Okay, these are the, so if you kick that tray as I did last time, the sound it produces is characteristic of that. If I change it, if I tighten it or loosen it or something, then it's going to behave differently. And the response is going to be different based on what the system naturally is. Okay, so it's kind of, it's what's called a natural response. It's what the system is going to be doing if you don't give it any additional input. You just give it some energy, and you say, okay, do what you want, and that's what's going to happen. So if I leave the classroom, okay, whatever you're doing then, reading your mail, chatting, talking, reading your textbook, whatever is your natural response. Okay, it's not a forced response. Okay, and that's also called the zero input response. This is what you do when there's nobody looking. Okay, or at least when I'm not looking. That's your natural response. Yes.
Why do you have a negative center of lambda?
Why do I have the negative? In the exponent there. Oh, sorry, I should take it back. Oops. Yeah, see, I take it. Yeah, sorry, because the roots are going to be d plus. Yeah. Yeah, sorry. I'm so used to thinking of exponent. Yeah, it is plus. It actually, the sign doesn't really matter, actually, as you'll find out. Okay, so that, yeah, but it should be, to be consistent with this, it should be, yeah, sorry, my mistake. The one thing I should point out is that where do these CIs come from, right? I never tell you where the CIs come from. The way that it comes from is that actually, at the end of the day, they're going to come from the XTs. Because what's going to happen is at time 0, we're going to match the outputs. So the CIs depend on essentially y0, y dot 0, etc., y to the n 0, which in turn depend on the x, on the xt on the right-hand side. So that's how we find what the CIs are. Okay, so I'm not going to go into that in too much detail. The reason is because the analysis of this kind of system, which is called the time domain analysis, is kind of finicky and not too much insight is there. And basically, nobody really needs to do it or does it. It's just a building block in the step for us to get towards transforms. So it can be done. People have done it, but I'm not going to go too much into detail. But I do want to talk about what happens when we have a complex response. So let's just do a simple example of the real response. And for example, if you consider if you consider this one, d squared plus 5d plus 6 yt equals 0, for example, is going to be an example of this, where pd is this. Then this is d plus 1 times d plus 5 y equals 0, and this gives us the equation c1 e to the minus lambda 1, sorry, e to the minus t plus, right, what am I doing here? This is not 1 plus 5, 3 plus 2. Okay, and that gives e to the minus 3t plus c2 e to the minus 2t equals is the response yt. Okay, so this is real. Okay, c1 and c2 are going to be reals, and the value we'll find will be from y dot and y dot 0 and y double dot 0 have to be given to you. And when you're given these two values, you can plug it back into these differential equations and figure out what the values of c1 and c2 are. And as I said, I'm not going to do that. But you can see that this is basically two reals. Let's just see what it looks like. c1 e to the minus 3t is exponential dropping off. It's a real exponential. It has no complex components. And it's going to drop off pretty fast, like this. And minus 2t is going to drop off as well, but less fast. So we have that, something like that. And then the sum of these is going to be an exponential as well. Okay, and again, it's going to drop off to 0. But it's the sum of these two things. So the sum of these two exponentials is going to drop off as well exponentially fast. So that's what it looks like over there. What happens when we have complex? This is the first new thing we'll talk about. Let's take the case where we have d squared plus 1 yt equals 0, and which we factorize as d plus j into d minus j yt equals 0. Okay, so here is where the first time we've seen where these lambda over here is complex. In fact, it's the simplest complex thing. It's just j. Then what we get is that the natural response is going to be yt equals c1 e to the minus jt plus c2 e to the jt. Okay, so we have these two things. So how do we visualize this? And here, the easiest thing to do is to simply replace this using the Euler's formula, right? You have minus jt and plus jt. And so let's just do that. So we get C1 cos minus t plus j sine minus t plus C2 cos t plus j sine t, right? And that's just expanding e to the minus jt as cos minus t plus j sine minus t, and e to jt as cos t plus j sine t. Now, we know, or we should know, that cos minus t equals cos t. Oops. It's and then sine of minus t equals minus sine t. This is just the equations for the, so using this, we can expand this as being C1 cos t minus j sine t plus C2 cos t plus j sine t. And if you expand that again, we get yt equals C1 plus C2 cos t, okay, plus j C2 minus C1 sine t, okay. So far so good, nothing really great. All we've done is expanded by Euler's formula. But the interesting part is when this refers to not a mathematical formulation, but a real system. Okay, when you have a real system of any kind, we know something about it, which is that there are no complex modes. In reality, there are no complex modes. We only have real modes. The imaginary J is imaginary in that sense. Okay, so any system, though we can represent it as a projection of a complex helix onto the real plane, in reality is going to have only real modes to it, right? So what we know is that this is going to be real, and this is also going to be real. Okay, this including the j is going to be real. Okay. So this is something we know. And so the two things we can assume we know about a physical system is that the response yt is going to be real, and it's going to be causal. Okay, causal meaning it has no value. It is 0 before time 0. At time 0, sort of the Big Bang, the world began. Before that, nothing. So we know that yt is 0 before 0. Okay, we're not going to use that fact over here. We're going to use this fact over here. So let's just say C1 equals a plus jb, and it will turn out that the only way to get this to work is C2 equals a minus jb. Okay, and if you don't do it this way, then we're not going to get the fact that C1 plus C2 is real and C2 minus C1 is real. So we need to have, we need to actually, am I doing this properly? C2 minus C1, or I think it should be, oh, yeah, that's right. C2 minus C1 is going to be minus 2jb, and then you multiply by the j over there, and you get plus 2. So C2 minus C1 is going to be, or j times C2 minus C1 is going to be real, right? This whole thing over here is going to be real only when the C2 minus C1 is going to have no real component. It's going to be pure complex, right? Only with a j. So given this, we can plug it in and find the values. But I'm going to note on this fact over here, which is that C1 and C2 are complex conjugates of each other by definition, right? We have some real part and some imaginary part, and the imaginary parts are exactly equal and opposite, okay? And we're getting this requirement because of the fact that we have this kind of form over here, and we're getting this form because we're getting essentially over here this notion that we have these two terms, minus jt plus jt, okay? And this comes from the fact that we have this plus j minus j, okay? So whenever we have this kind of form of equal and opposite plus j minus j, it's going to look like this over here. We're going to get complex conjugate coefficients for the for these terms in the time domain, okay, over here, yt. Okay. And we'll see this over and over again, that the responses, when they're complex, will be complex conjugate. Okay, because if they're not conjugate, we don't get a real response. Okay, and so I just want to highlight this, and then when we talk about control theory, you'll see, again, there's a reason why this happens, but you'll see that whenever we see complex numbers, they'll occur in conjugate pairs. Okay, and the conjugate, that makes it somewhat easier to analyze what's going on. The interesting point over here, from another perspective, is that this whole thing is actually, it's a real sinusoidal. It's a real sinusoidal response. It's real because it's causal, because it's real, you know, we kind of define it to be real, but it's pure sinusoidal. There's no complex components to it. Once you put the C1 and C2 in this form, the J's go away, and what we'll get is an oscillatory response. So what happens is you kick the system hard at 0, and it's just going to resonate, okay, or sorry, not resonate, vibrate with a pure oscillatory response over here, and it isn't decaying. Okay, there's no decaying component to it. It's just real sinusoidal over here. And so when this happens, well, it's like a guitar string. You have a guitar string, you pluck it, and it just it vibrates, pure oscillatory. Okay, and it may not. It's not a pure sinusoid. It could be, in fact, in this case, it's a sum of sinusoids, but in this idealized system, it doesn't decay over time. Once you pluck it, it keeps going forever. Okay, and what this means is that this equation over here is not a real system. Okay, it's a made-up system. So if you look at this system and say, oh, this can't actually exist, and that's why it looks like it's an eternal sinusoid for that reason. Okay, I've thrown a lot of things at you, so I'm going to stop now and just see, are there any questions? Yeah?
Could you explain again why C1 and C2 have to be complex
conjugates? Okay. I did a little bit of hand waving over there. What I'm saying is this: I have to come up with two numbers, C1 and C2, such that which are complex, such that their sum is real, and the difference is purely imaginary. Okay.
Why that requirement?
Because this is multiplied by j over here, and if you don't do this, then yt will have some value j associated with it. But yt is real because it's a real system. Okay, if I have a real system and look at the observe what yt is at any point in time, because yt is some kind of amplitude, right? Some kind of amplitude. If I plug a guitar string, I don't have any complex amplitudes. I only have real amplitudes. So, but nevertheless, in the solution for the system, I have some complex quantity. So that quantity must be multiplied by some pure imaginary value here, such that it goes away. It becomes a negative number, essentially. Right? So I have to get rid of that complex part. Okay. This is only true because it's a physical system. If I were to give you a mathematical object, which says here's a mathematical object, go ahead and analyze it, then I can't tell you the complex conjugates. Then it's just whatever it is, whatever the roots are. But because it's a real system, I can get this additional bit of information which tells me the roots are complex conjugates. So in other words, another way of looking at it is somebody tells you here are the characteristic modes of the system, okay, these are the characteristic modes. Then if you find that it's imaginary, one of them, then you'll say that's not a real system. Okay, that's not a physical system. Something else. I noticed that I'm kind of reusing the C1 and C2 perhaps more often than I should, because this one, these C's are not the same as those C's. Are they the same C's? Wait a minute. Yeah. Yeah, I should probably use. No, I take it back. Yeah, this should be something else. So this is. Yeah, I'm reusing those C1 and C2s a bit more than I should. But at any rate, some constants over here. These are the constants really. Am I doing it? No, they are the same. Okay, I'm sorry. I can't see that at the end of the board from here. But yeah, they are the same. Yeah, those are the C1 and C2 from these, which are these C1 and C2s as well. Okay.
So those C1 and C2 can be complex.
This one over here, this one has got to be real, because again, I'm claiming that this is a real system. Okay, if this is a real system, then C1 and C2 here must be real. When we have repeated roots like this, okay, then we have this j coming in, okay, And that j, because here I don't have any j. If you notice, I have pure real response over here. Okay. Yeah.
On your lecture notes, you wrote down the final equation as the lecture response is 2a cosine t plus j 2b sine t.
That's, oops, yeah, that's a mistake, yeah. That j is definitely a typo, sorry. It should be 2a cos b plus 2b sine t. Yeah, this clearly it's a, that's definitely a mistake, sorry. I'd better fix that. Okay. Okay, and then the last thing, and we'll take a break, is when I talked about this repeated roots. So I guess I didn't talk about your question. No, okay, the repeated roots, and I'll just give you the equation for that, and that's kind of if we have repeated roots, because we can have that from the polynomial, roots of multiplicity r. Then we have yt equals c1 e to the lambda t. So repeated roots, this is lambda, the root is lambda, and that means we have something like d minus lambda to the power r in the polynomial. Then we'll get c1 e to lambda t plus c2t e to the lambda t plus cr t to the r minus 1 lambda t, sorry, e to the lambda t plus the other terms which correspond to the other roots over here. Okay, so that's what that looks like. I'm going to just switch order a little bit and talk about stability first, and then come back to the system response to xt, because actually we already have pretty much everything we need to discuss stability. So let me do that over here. Okay. So I'm going to just state, and then I'll show you in just a minute, prove, I guess, something about a LTI system, which is that the LTI system, the way it behaves is dependent on the roots of this equation over here. Okay, the PD yt, the roots of this PD yt equals 0, the roots of the characteristic equation, which correspond to the characteristic modes, which is what happens when you give it an impulse response, impulse input at time 0, determine essentially how the system is going to behave depending on these roots. Okay, and so when we look at the stability of a system, I haven't actually said what the system is. Okay, and just as a aside, when you talk about the system, we actually have in mind two different systems. One system is the uncontrolled system. So we have a system which is we're just modeling it, we have no way to control it, and it's doing whatever it's doing. Okay, and the second system is the controlled system, where we're putting in some control input so that it has some proper behavior. For all purposes, stability response relates to the control system. Okay, so what is an example of a control system? Again, an example which maybe will make sense. Let's say that you're driving a car and you go over a pothole. Okay, there's a pothole, and so when the car goes over the pothole, there's a sudden sharp jerk. Okay, impulse input. Okay, and then after that, the car continues on. So that impulse, that sharp input, can be thought of as an impulse input to the system. And now we can think of the car having 2 or 3 different responses. And in your own experience, you probably experience these kinds of responses. If it's a car with a suspension that's very tight, very tight suspension, what will happen is you'll feel this big thump, okay, and you'll kind of feel it, and it'll kind of vibrate a little bit, and there'll be a sharp jerk, but it'll kind of stop. Okay, it'll be just this very sharp. On the other hand, if you have a big car or a truck or something like that, a really big old car, you won't have the sharp jerk. You'll have a response, but it'll kind of take a while for it to die down. Okay, and eventually it will die down. Okay, so it's a control. What's happening is that your shock absorbers are essentially a control system. Okay, we can talk about the response, and we'll study the exact difference between these two mathematically in a little bit. But intuitively, what's going on is that we're given some input and we have some response. It really doesn't depend on the nature of the input. Okay, it doesn't really depend. It's input. It's some sharp input, but what the response is going to be characteristic of that system. Okay, if it's a big old car which has a lot of weight on it, it's going to have that smooth and slow response, no matter whether the pothole is one pothole or your bad road. Okay, it's going to have that smooth response all the time. Whereas a sports car is always going to be kind of jerky no matter what. So that's why I call it the natural response. And they all depend on the roots of this equation over here. And it falls into basically three categories. So these roots are of the form lambda, which belongs to complex. So it's a complex number. So it looks like sigma plus j omega. And just look at one root, this particular one. Let's say sigma is greater than 0. Then the root is going to look like c2 sigma e to the j omega t. Now this is a helix. And if you note, if sigma is greater than 0, it's a helix that grows larger and larger over time, right? So what's happening is that we kind of have this helix that grows bigger and bigger, and this is going to be uncontrolled and bad system. That's your Tacoma-Narrows bridge, okay, where the modes are growing. The sigma is greater than 0. So anytime we have a root of this such that if any of the roots has a sigma greater than 0, we're going to have a system that is whose response yt is growing with time. Okay, that's bad. Okay, so it's unstable. Okay, so we call such a system unstable if any sigma greater than 0. So that's the first rule. If any sigma, it's unstable. Okay, so if all the sigmas are less than 0, we're in good shape because everything is decaying down exponentially fast. Okay, you get an input, it's going to go down, right? Yeah?
Yeah, at the very last line, you missed the coefficient of t for sigma.
Oh, sorry, yeah, sigma t, thank you. So if any sigma is greater than 0, we're going if all sigmas are less than 0, then it's stable. Okay? Because everything is going to die down. Because we have this strong e to the sort of minus something t forcing function. This is just oscillatory. That's just sinusoidal. Its magnitude doesn't change over time, right? It's just cos omega t plus j sin omega t, whose magnitude is always 1. It's a phasor of magnitude 1 rotating round and round, okay? But we're modulating it with e to the minus t, e to the minus something t. And the bigger sigma is, the faster it dies down. So what's happening in a sports car is sigma is very large and negative, okay? So it just goes right down, okay? Whereas in a Cadillac, okay, the sigma is small and negative, so it doesn't go right down. It takes a while to kind of glide down, okay? Now, if all the sigmas are 0, then what happens is we have basically everything neither positive nor negative. So this term essentially is 1. This term is just 1, right? So then everything depends on this e to the j omega t. If we have just one root, if you have one, to be more precise, if you have one, so if it's on the j-axis, okay, this is the real axis, this is the imaginary j-axis. If it's one root on the j-axis, we know it's going to be complex conjugate. So you're going to have two roots actually like so on the j-axis. Okay, they're going to be complex conjugate reflected about the real axis like that. If you have one root like this, then it's going to look like essentially like this one over here. C1 plus C2 cos t plus sin t. It's going to be oscillatory and never die down. Okay, so we call this marginally stable. Okay, it's not exceeding, it's not shrinking, it's just staying where it is. It just keeps oscillating round and round. Okay, like a guitar string. Okay, without any dampening, it'll be the guitar string. So if all sigma equals 0 and non-repeated, then it's going to be marginally stable. And if you get repeated roots which are also on the j-axis, then we get this where did I put it? So this was this thing over here where we have the t e to the, so we have c1 e to the lambda t plus c2 t e to the lambda t plus, so when you get this one over here, the t term, that's growing with time, right? When you get repeated roots over here, you get growing with time. When you get growing with time, then at that point, we're going to have unbounded system. So remember, this one over here corresponds to d plus j, d minus j. So these are not repeated roots. These are just complex roots, right? When we have repeated roots, then we get the repeated complex roots, then we get two of these, one on top of each other, and then we're going to get the system that's unstable. So we have kind of 4 cases. All the sigmas greater than 0, or any sigma greater than 0 unstable. All sigmas are less than 0, it's stable. If all sigmas are 0 and we have non-repeated roots, it's marginally stable. And all sigmas is 0 and it's any repeated root, then we have unstable again. Okay, and so we can just take the system, express it in this form, PD equals 0, PDYT equals 0, compute the roots, and then immediately tell whether the system is stable or unstable or marginally stable just from that. So this modeling of the system as PDYT is extremely important. Okay, it determines what's going on. That's the, so again, the intuitive reasoning behind stability, and then we look at this in somewhat more detail. Okay, repeat this actually 2 more times, because this is really one of the, this is at the heart of control theory. How do we get this to work? Okay, so in short, what we want to do is to choose the system parameters such that all the sigmas are going to be less than 0. Okay, and that's what we, and the value of the place where sigmas is called a pole of the system, and so we want the poles to be placed in the left half of the complex plane. That's what's called pole placement. Okay, we'll come back to that. Okay, any questions about this? Yeah.
What if some are greater than 0 and some are less
If
than 0?
any sigma is greater than 0, it's unstable, because that's a mode.
Okay,
Yeah,
right.
if any sigma is greater than 0. Yeah. Any other questions? Okay, so moving on, I'm going to now talk about the response to the to a non-zero input. Yeah.
If all are 0 and 1 is less than 0?
If all are 0, right, it means if it's repeated or not.
Except for 1?
Yeah, that's okay. If it's less than 0, just ignore it, because anyway that's going to die out.
Okay,
Right.
so just the remaining ones.
Yeah, the remaining ones, yeah. So we basically, yeah, we're looking at the ones that are possibly going to cause growth. So if it's repeated roots, then we're in trouble. If they're not repeated, then we're going to be marginally stable. So some modes will die out, other modes will persist. If you hit a piano key, for example, some harmonics will die out quickly, and some harmonics will sustain for a longer period of time. Okay, if one of them sustains forever, that's going to be on the j-axis. Okay, so stability. Let's look at the response to, so the equation that we have for a LTI system, not for any other system, LTI system is what's called total response equals 0 input response plus 0 state response. And that's not in the text. I'm just I don't want to put too much in there, but anyway. So this what we looked at is so far is 0 input response. Now we're going to look at what's called 0 state response. That means in the beginning of time, we're assuming that the system is 0 state, and I'm not going to explain exactly what 0 state is now. We can define that precisely, but you can think of it as initial conditions are, there's no energy in the system. It's quiet. Nothing is happening. We're going to go through a little bit of mathematical, I won't say trickery, but a few steps that are a little bit, each step by itself is easy, but when you put it together, you get a very important and nice result. So I'm going to go through that. It's similar to the 0 input response, so I'm going to go through that. And to do this, I'm going to use a new notation, which is this arrow over here, and let's call that leads to. And so we're saying this input leads to this output. okay? And that's just the notation over here. So I'm saying if I give this input, remember I want to look at the response to some input xt. So I'm going to give you some input, and then I want to tell you what the output is, okay? So I am assuming, write this down, assume you are given the impulse response. Impulse response, which is denoted h of t, and defined as delta t leads to h of t. In other words, the system in the middle, okay, so the system is sitting over here. It converts this input to that output. So it converts, if you give it an impulse delta t, it's going to give you an impulse response h of t. It could be complex. I don't really care what it is, okay? And how do we compute this? Well, this delta is at 0, right? At time 0, it has no input after time 0. So this impulse response is basically the same thing we got by doing the 0 input response, okay? Because it is a 0 input after time 0, okay? So the only difference is that to compute h of t, I have to figure out what the values of C1 and C2 and all those things are, okay, which I've ignored, okay? But when you do that, what you get using that previous step is to get h of t, okay? And I'm assuming you already figured it out, and you need the initial conditions and so on to compute h of t, okay? All right. So we know, again, this is by definition from last week, that xt delta t, okay, is equal to x0 delta t. And this is just saying that if I take delta and I multiply it with any function xt, it's selecting out the 0 value. Everything else doesn't really matter here, okay? And to be more precise, what delta t is, okay, delta t has infinite power and unit energy. Okay, that's the easiest way to think about it. And what I mean by infinite power is that the spike goes up to infinite. That's what we define by power. Okay, that's the meaning of power. What is energy? Energy is area under the curve. Okay, when you get your electricity bill, you say, okay, my electricity, my iron is consuming, let's say, 1500 watts. 1500 watts is the power. Okay, but the amount you billed for is actually for energy. Your 1500 watts over 1 hour is 1500 watt hours. That's 1.5 kilowatt hours. And if you're doing it in the middle of the day, it's going to cost you 10.9 cents. So if you keep your iron on for 1 hour, it's going to cost you roughly about 15 cents, 16 cents, something like that. Okay, so that's energy. In the same way, the delta, the power is tending to infinity. Okay, it's going up. But the energy that's consuming is, because we chose the height to be 1 over t and the width to be t, the energy is only 1. Which means that x0 delta t can be viewed as having an energy of x0. That's why we say it's scaling. x0 units. It's not the power that's scaling as much as the energy that's scaling. Again, we're working with delta, which is this mysterious thing. So, but I'm just trying to give you some intuition about the meaning of what we see, what happens when you see x0 delta t. So we can say that since the input is going to be this, if the input is xt delta t, so let's use a leads to here, xt delta t, what does it lead to? Okay, and this is where sort of the magic comes in. And I'm saying delta t leads to ht, and x0 delta t is sort of the scaled input, right, over here. So this should lead to x0 h of t. And why? Because delta t is leading to ht, and I'm scaling the input on the left-hand side by x0, so right-hand side is going to look like the same scaling over here. Okay, that's the intuition over here. And okay, so I'll stop. Are there any questions about this particular step? Because once you agree to this step, the rest of it is just straightforward. But this step is kind of the tricky part. Okay. Okay. And to be perfectly honest, the way this is done in almost every textbook I've seen, including mine, it's kind of hand wavy. We kind of suddenly introduce this leads to notation. The reason is because the actual mathematical description of this is messy. Okay, it includes deltas, which is not really a function. Okay, and we're trying to do this. The step over here is mathematically problematical. Okay, to get it right, you have to introduce a lot of additional math. So all the engineering books just say, well, intuitively it's clear this is correct. Okay, and then there's one more step where you have intuitively it's clear, but the mathematical details are actually pretty messy. And so anyway, we're going to jump from here to here, assuming that you agree that this is scaling the delta. And so when you scale this, when you have the input of delta, you get h, and you scale the input by x0, then the output is going to be scaled like that. In which case, we can now use this equation. So we have this. We know that xt delta t minus tau, okay, equals equals x tau delta t minus tau. This is something I wrote earlier. All I'm doing over here is saying that the time shifted impulse is picking up just one value, which is the tau value. Okay, by definition of delta as being a selector. Okay, this is just repeating the old thing. And so using the same kind of inference, we can say that x tau delta t minus tau leads to x tau h t minus tau. Why? Because you see over here, if I take delta over here and I'm going to time shift the delta, then the only thing that matters is x tau, and then the output is going to get scaled to become this one over here, right? And then finally, I know that xt, so I know this, I'm just going to write this on the side, xt equals integral minus infinity to infinity x tau delta t minus tau d tau by definition, which means that if I essentially can integrate both sides to get xt leads to the integral minus infinity to infinity x tau h t minus tau d tau, which is equal to xt convolved with h of t. Okay, again, that's definition, by definition of convolution. So, okay, so let me just go through this over here because the derivation is now all written out. We start out by saying that delta t, if you give it an input, it leads to the response h of t. That's by definition of what h of t is. You're given the impulse response ht, so you know ht. Okay? Somebody gives it to you and says he's ht. Then we say that by definition of impulse, xt delta t is same as x0 delta t. So if you take any function xt and we multiply it with the delta t, what we're going to do is just select out the value of x0, and you're going to get a scaled impulse of energy size sort of x0 delta t. Okay, so it's going to have an energy of x0, and it's going to have, of course, infinite power, but the energy is going to be x0 by definition of the impulse. And so if you're given this input, what you're doing is you're scaling the input by essentially x0. You're scaling the input by x0. So the output is going to scale by x0. Why? Because it's linear. It's a linear time invariant system. So if you're scaling the input by any value x0, which is essentially a constant, the output is going to scale by that as well. So we get xt delta t leads to the scaling of the output by the value x0, x0 to ht. Now we want to know what happens at the next instant in time. So we introduce tau over here. We say, okay, let's say we multiply xt by delta t minus tau. Well, this is just scaling the impulse located at the time tau, because when you subtract tau, you're pushing it to the right by tau. It just chooses the tauth value of x. Okay, we're going to select the tauth value. That's why delta is a selector. It selects the tauth value of x. So this means that if you multiply, if you take the x tau delta t minus tau as the input, again, because it's time invariant, the parameters don't change, I must be basically getting the tauth value of the impulse response over here, which is x tau multiplied by that. Okay. And then at that point we can say, so basically we're taking this whole system over here and just shifting it to the right by tau. Okay, and that's why we get input is shifted, time shifted. The output is going to be time shifted, because if you compare these two, we are just time shifting the input. X0 ht means if you shift it by tau units, xt is going to be ht minus tau. So I can get it that way as well, because it's time invariant. And I'm getting this one from this one over here from linearity. So if I take these two together, I know that xt is just the sum of these x tau ht minus tau. Sorry, xt is this over here. Xt is the x tau delta t minus tau d tau. So if I do this, the right-hand side is going to be the same thing. I'm going to take the integral with respect to d tau. Okay, so you can think of the input as being chopped up into tiny, tiny segments of size, d tau. And each tiny segment of d tau is going to have an output corresponding to x tau ht minus tau. Okay, that's the corresponding output. So the overall output is going to be this, and so we get xt convolved with ht. Okay, so this is a huge result. It's a huge result because what it's saying is that I am giving you ht, and no matter what the input xt is, as long as the system is linear and time invariant, the output is going to be the convolution of xt and ht. Okay, that's it. So I give you ht. So in some sense, the system is completely defined by h of t. How did I compute ht? I computed using the zero input response, right, by setting pd equals 0 and so on. Computed h of t that way. Once I give you that, you essentially know everything you need about the system, because for any input, I just take the convolution over here, and that's going to tell me what the output is going to look like. So that's going to be yt. It's going to look exactly like that. So in the homework question, okay, therefore the answer looks something like this, just to give you some examples. So there we said that the response was yt is equal to, for the zero input yt was what? C1 e to the t plus C2t e to the t, because it's a repeated root. So therefore the output for this input is going to be yt equals this one over here, C1 e to the t plus C2 e to the t e to the t convolved with 0.5 e to the minus 0.25 t, because that's the input. Beg your pardon?
E raised to power
Minus t, sorry. Yeah, that's right, yeah. Okay, so the minus t. That's the answer to the first homework question. So once I've given you ht, which is this one over here, all I need to do is convolve it, and you're done. Now the convolution is not easy to compute. Yeah?
The order doesn't matter?
No, order doesn't matter. Convolution is, because it kind of, you flip around either way and slide it, yeah.
Can we show it as an integral?
Integral?
Yeah, an integral form?
Over here?
Yeah.
There's no integral. I have two functions of time function convolved with another function. I'm doing the convolution of two functions where there's no integral. I mean, you can write the integral if you want. You could write out the integral as being minus infinity to infinity. This one would be C1 e to the minus, so t plus C2 t e to the minus t, 0.5 e to the minus 0.25 t minus tau d tau. Okay. So basically writing it as x tau delta t minus tau, so sorry, v t minus tau. If you want to write it in that form, this is x of tau. Let me see, x of tau h of t minus tau d tau. Right? I could write it in this form. So, but why bother, right? This is easier to write over here, but it means the same thing. Yeah.
If we calculate the impulse response using Laplace transform,
Yeah.
we'll get the delta in HFT.
We're not going to talk about Laplace transform yet. But yeah, so this is a funny system. It's actually a it's yeah.
So which, if we have delta in the answer,
No, the answer I'm looking for is just this one over here. Okay, I'm not expecting any Laplace transform and so on because I haven't covered that yet. Okay. Any questions about this? Yeah.
XT should come first in the convolution.
XT should come first in the convolution. So the thing is, the convolution, the order doesn't really matter whether you do XT, HT, or HT, XT. It's the same thing. So it's luckily for us, convolution is actually symmetric. Okay. Any other questions? Okay. So. How many of you have seen sort of or used transforms before? Just want to raise your hand. Okay, just raise your hand a bit higher. Okay, so about 2/3 of the class has actually seen transforms. Let me now change the question. How many of you think you understand what a transform is? Okay, 1, 2, 3. Okay, so you guys can sleep, the rest of you. I was introduced to transforms as an undergrad in my undergrad course in systems, signals and systems. When was it? 1982, I guess, or 83, something like that. Probably 82. And honestly, I don't think I understood a word of it. My instructor came to the board and said, "This is a Laplace transform," and wrote it down. And I said, "Yeah, sure, whatever." Copied it down, and I had no idea what it was. And then I went to grad school, and I studied control theory. And so again, same thing. I was in the Z transform, and I said, "Oh, I vaguely remember it. I get a headache thinking about it." And but I said, "Okay, fine. I'll go through it." And I wrote it out, and I did all this. I did all the math, and I thought I knew what it was, the Z transform. And immediately after grad school, I didn't work in control theory anymore, so I didn't have to look at it. So I said, "Thank God it's over. I don't have to worry about that anymore." And I started writing this book. And I said, "Okay, I have to cover control theories." So I went to my grad notes and I looked at the section on transforms, and I had that big headache all over again. I said, "Oh boy, I really wish I didn't have to cover this because I don't understand a word of it. I just can't remember." I mean, I said, "Yeah, I have all this stuff. It's my handwriting. I must have done it, but I have no clue, what's going on here." I'm just it was just awful. In fact, when I was teaching this course in 2008. My hope was to cover control theory as part of the course. And I opened those notes and took one look, and it was so awful. I was traumatized. And I said, "No, I'll cover statistics instead." So which is what I did. I changed it from control theory to statistics. But finally, about a year and a half ago, I guess, I said, "Okay, I just have to do it." So I just kind of sat down with the book on transform domain, actually 3 or 4 books. And finally, I got it. Okay, I finally got what it is all about. And what I'm going to try and do is to explain to you transform domain techniques and transforms in such a way that you'll never forget it. And what's more, you won't even be scared of it. It's going to be really intuitive and easy. And hopefully, that's what you'll say at the end of next week when we'll be done. Okay, but so before I kind of get into that. What I want to, I guess, the end of that prefatory note is that transforms are a little bit complicated. They are a bit funny to work with, and often a subject people are scared about, mostly because it hasn't been, I think, introduced or taught properly. And I'm going to try and teach it to you, quote unquote, properly. Properly meaning, from my perspective, right? Basically, I've been doing system design, hardware systems, software systems, whatever, for 20 years. And I see this math, and it scares me, right? So I want to make it, I know that's a perspective you guys also should probably have, okay? And so I'm trying to get it to you from that perspective of what is it all about. Okay, so before I go, so why do we do transforms? The reason is, the 3 reasons why transforms are good. One is that it converts a convolution to a multiplication, okay? So we saw this, that convolution is this important thing. And if you take 2 functions and we want to convolve them, we can give the output. So this is beautiful. I give you h of t, the impulse response. How do I get h of t? I just kick it hard. I take a photograph. I figure out what h of t looks like. I basically can draw you a function of h of t. And then I say for any input, no matter what it is, I'll tell you what the output looks like. Very nice. But I need to convolve it, and that's hard. The second thing is it converts basically this y dot and y double dot and all these other things into plus, okay? So it converts differential equations into algebraic equations, okay, and that's very nice as well. It makes it much easier to solve systems for differential equations. We can just solve algebraic linear systems instead. And the third thing is that it gives us this input into the natural response. Okay, we get this insight into where are these lambdas. Remember I said these characteristic modes are really where everything is happening. So I can tell you kind of the characteristic modes just by looking at the transform. It turns out to be quite easy to do it that way. So the natural response is very important, and the transforms give us input into all of this. So that's why it's worth understanding. Now all of these kind of don't make sense right now, but this is just a preview of why it's very important. Many of you will continue on to doing thesis that might include other kinds of transforms. So I'm going to talk about 5 transforms: the Fourier series, which is the sort of the original idea, then the Fourier transform, then the Laplace, sorry, the discrete time. Actually, it's a discrete time and space, actually, but we never mention that usually. Fourier transform, and the Laplace, and then the Z transform. So these are all transforms, and they operate on basically different kinds of signals. And there's a table which tells you what the types are: continuous, periodic, aperiodic. So it's basically continuous or discrete, okay, and periodic or aperiodic, and that tells you what's going to happen. And then the output, what it produces, is either a sum of sinusoids or the integral of sinusoids, okay. And so again, I'm not going to go into much detail because it doesn't make sense until you've seen all of them. There's a table for you to keep track of. But we'll start with the first one, okay? And then all of these things hopefully will become a bit more clear. So I'm going to start with the Fourier series, okay? And hopefully we'll cover it in the next 20 minutes, and then because it's really not that complicated. And I'm going to set the stage for it by saying, what was in Fourier's mind? What is he trying to do? Fourier was studying music, okay? Essentially, he was looking at musical strings. He was looking at strings that are plucked, piano strings or guitar strings, harp or lute or any of these things. These are all strings. You pluck them, and then they vibrate, and then they die down, okay? And that's basically it. Now, when you have this kind of a plucked string, we know that it has this kind of notion. You have this one node, and then you can also have, it can have this kind of nodes, and it can have many nodes. And these nodes are places where the string is not moving, okay? It's kind of fixed point. It doesn't move, okay? And if you ever had you and a friend have a rope, and you've probably done this as a kid, you have a rope and you swing it, or you can have 2 modes. You can have, it will be a fixed point in the center that's not moving. It's the same kind of deal, right? And so Fourier was interested in this because it's a kind of why is it not moving? What's going on here? But his analysis led him to the following conclusion. I'm not going to go through the historical development, but he considered these functions which we can think of as eternal periodic functions. And what we mean the eternal is that they have no beginning and they have no end. And the periodic means that we can define some time period, and we'll give it the notation T0. That's the duration. And whatever signal is there in this period, okay, is going to be exactly replicated again in T0 again. So this whatever signal, is going to come like that, and then it doesn't matter, but it's going to repeat itself over and over and over again, forever, okay, from the beginning of time to the end of time. Then you can say, yeah, this is kind of silly, it's never going to happen this way. And you'll say, that's fine, we'll just study this because it's easy, and then we'll make it less easy in a bit. So given that it's eternal periodic with a period of T0, okay, what Fourier showed was it's possible to represent this function, okay, any one period, okay, as the sum of sinusoidals. So we have a sine wave plus a sine with a double the frequency plus a sine at 3 times the frequency plus whatever. and so on, with different weights. Some are bigger, some are smaller, but you add them all up and you'll get this. Okay? What is the period? This period over here, from here to here, is going to be basically T0. They're all going to be periodic. Okay? So this one is going to be T0, okay, from peak to crest. As you can see, these T0s are shrinking. Maybe I should call this T0 by 2, this T0 by 3, and this is T0 by 4, etc. Okay? They're all called harmonics of the base period over here. And in fact, what we do is, to make our life simple, we define omega to be equal to omega naught equals 2 pi by T naught. And this 2 pi factor comes in because we have to worry about 360 degrees versus radians. So in one full cycle, we have 2 pi radians. And so it turns out to be the factor that we need. And so we can say this has a frequency of omega naught. This is going to also be omega naught. This is going to have frequency of omega naught, 2 omega naught. This is 3 omega naught. This is 4 omega naught. Okay? And so on. Okay? Actually, it will be infinite. We can go up all the way up to infinity. And at infinity, or let's say 10,000, we have very, very, very high frequency, right? It's 10,000 omega naught, whatever the base frequency is. It's really very, very narrow sinusoids over here. Okay? You better wake him up. He's going to miss something important. Yeah, you. I'm going to bring you a cup of coffee next time. Okay. Okay. So this is the beautiful intuition behind Fourier's analysis, which is that if you take something with an intrinsic period of omega naught, which is 2 pi by T naught, we can represent this arbitrary waveform as a sum of sinusoids. Okay? Now, there is sort of a footnote to this, which is almost at every point and almost all waveforms. Okay? So there are some waveforms which are pathological, which cannot be represented in this fashion, and there are some points in time where they cannot be represented. So for example, if you take this one, the square pulse like this, it turns out at this point in time, getting that exact value, because it's such a sharp transition, getting it to be sum of sinusoids is a bit hard. Okay? And it turns out even if you have many, many, many terms, it still doesn't match very accurately. We have approximately a 10% deviation. This is what's called the Gibbs phenomenon. Okay, and Gibbs is a famous American chemist, and then there is a law that says every law in mathematics is named for the wrong person, and this is also named for the wrong person. Gibbs was not the person to discover Gibbs phenomenon, but at any rate, that's the name that happens, that's given over there. And so that's the intuition behind the Fourier series, which is that we can represent this complicated periodic waveform as a sum of sinusoids. Now, why do we like sinusoids? Because remember, this input given to a LTI system is going to be a scale output sinusoid. Okay, you take a sinusoid, put it into LTI, comes out being just scaling, no nothing, right? Because you could say this is an eigenfunction. This is an eigenfunction of the LTI, and the LTI system obeys superposition. So we take this output, this output, this output, this output, sum them all together, and we get the output. So we have this complicated input over here. We break it up into pieces. Each of these is an eigenfunction. We just do a scaling. We get output, and we know what the output is. So that's beautiful, right? It makes life much simpler. So that's the intuitive reason why we care about it. So I didn't tell you something, which is I have, in addition to these periods, I have some scaling going on. So I'm going to have some scaling by some factor, let's say A1, this is A2, etc. So let me just write down the math, and then the scaling factors will become clearer. So I'll write down the two ways of expressing the Fourier series. And the first one, which is what Fourier wrote down, is something like this. If xt is given by, the xt is the function over there, a0 plus, this is the sum of the k equals 1 to infinity, ak cos k omega naught t plus bk sine k omega naught t. Okay? And so we see that we actually have at each frequency two two sinusoids. So I kind of lied to you. I told you it's just sinusoids at one frequency. Actually, we have two. One is the cos k omega naught t, sin k omega naught t. But the important thing is that the frequencies are k omega naught, which means that the frequencies are integer multiples of the base frequency, where omega naught equals 2 pi by t naught. Okay. So that's now. What are the AKs? So we're given A0 is given by it's what's called the DC component. Is integral 0 to t0, or actually any span of t0 will do, 1 over t0 xt dt. This is the average divided by t0. That's just the average energy in the signal. So if you take the signal over here, this average energy is say somewhere over there. So this value is going to be A0. Okay, that's a DC component. Okay, if you take the signal, put it through a very low pass filter, what you're going to get out of it is going to be the DC component, and that's going to be A0. And then AK is given by 2 over T naught, integral 0 to T naught, xt cos k omega naught t dt, and BK is given by 2 over T naught, integral 0 to T naught, xt sine of k omega naught t dt. So we have explicit values for AK and BK depending on xt. So if I tell you what xt is, I basically multiply xt with the k omega naught t, which you'll recognize as being the kth term anyway. So we're going to multiply xt by the corresponding frequency, okay, and take the integral, and that gives you AK. Similarly, you do the frequency, take the integral, gives you BK, and then we plug it in over here, and basically you get what xt is. Okay, so we are roughly speaking taking the integral of the product of the function with the basis function here, k omega naught t, or sine k omega naught t, and you get that over here. And there's some normalization going on over here with the multiplier over here. Okay, any questions about this so far? Okay, so then we can do a little bit of math to make that form simpler, because that form so that form I should add that AK and BK are reals. So AK is, well, for all k, AK, BK belong to the reals. So those are all reals. I can now use a little bit of math to reduce this to a simpler form by allowing the factors to be complex. Okay, and actually, in the interest of time, I'm going to let you just read it in the book, because the derivation is absolutely straightforward. All you're really doing is replacing cos and sine by the corresponding. So we're just replacing cos k omega naught t equals e to the j k omega naught t plus e to the minus j k omega naught t by 2. So if you do that substitution and a similar substitution, sine is going to be sine k omega naught t, which is this one over here, right? We can replace that by the difference of two exponentials using Euler's formula. Then we can get the following thing. We get xt equals integral k equals sum k equals minus infinity to infinity, ck e to the jk omega naught t, where ck is a complex number, okay, and is defined to be ck equals integral 1 over t naught integral 0 to t naught xt e to the minus j k omega naught t dt. And what you're seeing over here is that the basis function has changed from the cos or the sine to the e to the minus jk omega naught t, right? You see over here, cos k omega naught t dt has now become e to the minus jk omega naught t dt. And because we get this divided by 2 over here, that actually cancels out the 2 over here, which is why we get the 1 over T naught for Ck rather than 2 over T naught, okay, because that goes away. And this is a fairly straightforward derivation, and I actually encourage you to go through it so that you can see how that's done. And so we get a very simple form for the Fourier series. It's just this. It's the sum, an infinite sum, of some constant multiplying a complex exponential, which is just what we wanted. We got a bunch of complex exponentials, each having a period of k times omega naught t. Now you notice that the period is actually negative as well. And the reason it's negative is because we can now think of the phasors as going faster and faster in this direction or in the other direction. Okay, and we are just looking at those frequencies as positive and negative frequencies. So that shouldn't really confuse you because we know what that means. So you have the positive frequency and the negative frequencies, and you sum over all those frequencies, and we add it all up. What Fourier showed was this gives you exactly xt. Okay, and so we have essentially got a bunch of scale phasors. Now the part where it gets a bit messy is that we are not scaling by real quantity. We're scaling it by complex quantity. And again, when we scale by complex quantity, what it really means is you're going to multiply this complex value with this complex value, and that gives us a certain output, whatever that is. And intuitively speaking, multiplying by complex quantity means that we are both going to change the magnitude and the direction. Okay, the magnitude is going to change, increase or decrease, and the direction of the angle, the angular phase is going to go left or right. So it's going to change what's called the phase angle, but we'll get to that when we do some derivations. For now, let me just give you an example. I'll do the homework problem. And what we had there is an eternal series of pulses, and the pulses are of width 2 seconds, and they repeat every 10 seconds. So this other pulse over here, and the center to center is 10 seconds. And I wanted you to find what is the value of Ck, and the height is 0.5. And I wanted you to find what is Ck for the kth term. So how do we do this? You basically just plug it in. You just plug in the values, and you'll get the answer. So what is Ck? Ck is going to be 1 over T naught integral. So we can choose any integral time. So we just make it easier. We'll go from basically -1 to 1, okay, because we don't really care what the what span it is, and it will be e to the minus j k, and we cannot just 2 pi by T naught equals 2 pi by 10. Okay, we'll just leave it as omega naught for now, and omega naught t dt. Okay. Yeah, sorry, times 0.5. So that'll just go over here because xt is 0.5, right? In that range. It's C0 otherwise. So this integral is all we care about. And this will be given if you just plug the values from the solution. Actually, the answer, I'll just write it down for you, is basically 1 over j k omega naught t naught, which is 10. It's going to times e to the j k omega naught, because okay, minus e to the minus j k omega naught. Okay, because this integral is just going to, it's just e to the x, right? E to the x, so e to the kx, the integral of e to the kx equals 1 over k e to the x. That's it. It's really trivial. So you just put that in the denominator, like so, and then we evaluate it at the values 1 and minus 1, and you get that. And this is equal to actually, I'm going to give you the answer because I know I'm running out of time. So you can grade it, and I did compute it. It's in my notes right here. So it's going to be 1 over 10. And we can use Euler's formula on this to get sine. And the term inside is going to be 4k times 4 pi over k times 4 pi. Okay. So, and if you want to really make it simple, it will be 0.1 sinc of 4k pi. And that's the smallest possible answer, but this is an answer that's acceptable. That's also acceptable, okay, as answers. Okay, and I introduce here the sinc function, which is given as sinc x equals sine x by x. Yeah.
Have you simplified that 0.5?
I just took it 0.5. Well, I have the, how did I do it? So it's, ck is half times 2, oh, wait a minute, did I do 2 over t naught? That's right, tau equals 2, sorry, I'll just write this over here. Tau equals 2, t equals 10, okay? So we get tau over t naught is going to be, there's a 2 factor that cancels out somewhere, I think. 1 over 2 times 2 over 10. Is somebody getting different answer from this, or?
We'll have the 0.5 on top and 2.0 is 10 on the bottom.
2.5, yeah, so, yeah, so 0.5 over 10. So why am I getting 0.1 over here? I think I'm making point, just a second. I'm going to give me a second over here. The value I was using was tau over t naught. Yeah, so it's 2 over 10. Sorry, it's 0.2. I mistake. Yeah, I'm sorry, what? Oh, yeah, because I'm doing this 4 pi over here as opposed to 2 pi, right? So I'm going to get tau over t naught, so it's going to be 1 over 5. This is going to be 0.2. I want to get the 4, otherwise it will be 2 pi, right? Okay. So this is the correct value, sorry. 0.2 sinc 4k pi.
Suppose if we take the integral from the range 0 to 2, we'll get a different answer.
If,
The way we
yeah, if you take the integral from 0 to 2, it should simplify to this, because the terms of the Fourier series are independent of which span you take. It will look more complicated. It won't look as simple as this, but it will be equivalent. Okay, so 0.2 sinc 4k pi, or 1 over 5 k4 pi, or 1 over 10 k4 pi over 2 pi k. All of these are valid answers. Okay. Any questions? Yeah.
Can you just, like, you have this equation 35 for example.
Yeah.
Can you just use tau and
T.
0 from
Yes, you can. That's pretty much what I did. So I said, as long as you said tau equals 2, t equals 10, and you plug it into 35, and divide and multiply by 0.5, because the amplitude is 0.5, then you should get the answer.
like
You got a different answer?
basically got sinus k w0 by 5 k w.
Sine of, what is it? KW0
By 5 k w.
sine, well, there should be why am I getting a pi? Wait a minute. K, just a minute. Tau by, just a second. There's no pi over here. Okay. I think I messed up my solution somehow. How did I get that? Oh, right. Because omega naught is going to be 2 pi by 10. That's why I get the pi over here. So you left the omega W0 or omega naught as omega naught, right? Omega naught should be substituted as 2 pi by 10. So my answer is correct. Okay, let's stop here. And then anybody who has a different answer, just come to me and we'll discuss it, okay? Because some of you need to leave.